Good morning,
Sir,
Professor
morning,
sir.
sir.
Good morning.
Morning. Morning. Goday madam. Goday madam. ட்ரையல் பார்த்துடலாமா சண்முகம்?
பார்க்கலாங்க சார்.
பார்த்தீங்களா?
Good morning, sir. ப்ராப்ளம் தெரியலையே, வேற சொல்லி கூப்பிட்டாங்க.
சார் உங்களுக்கு ஸ்கிரீன் ஷேர் ஆகலைங்க சார். சார் நீங்க மியூட்ல இருக்கீங்க சார்.
Sir, good morning. This is Kode from Kongu.
Good morning, madam.
Good morning, sir. How are you, sir?
I'm fine, madam.
Fine, fine.
சார் ப்ரொஃபசர் சார் உங்களுக்கு வந்து மியூட்ல இருக்குங்க சார் ஃபோன்.
சார் உங்களுக்கு மியூட், உங்க மைக் வந்து மியூட் அன்மியூட் பண்ணோம் சார்.
சார் உங்க வாய்ஸ் கேட்கலைங்க சார்.
ஹலோ, இப்போ கேட்குதுங்களா?
இப்போ கேக்குதுங்க சார்.
ஸ்க்ரீன் ஷேர் ஆகிறது எப்படி மறந்துருச்சு? இப்போ ஷேர் ஆகுதுங்களா ஸ்க்ரீன்? சண்முகம்
சார் ஆகுதுங்க சார்.
ரோல் ஆகுதுங்களா?
ஆகுதுங்க சார்.
ரைட், ஓகே. மேடம், காலேஜ் எப்படி போயிட்டு இருக்குங்க? கொங்கு இன்ஜினியரிங் காலேஜ். கோதை மேடம்.
Sir, shall we start the session, sir?
Okay, we'll start.
Good morning to one and all. I welcome Professor and participants to the first session of fourth day. Today's topic is advances in fiber reinforced concrete. Professor Dr. G.S. Triyanam is known to all. He is well versed in fiber reinforced concrete. Institute of Road and Transport Technology. They are having a very good structural testing facilities. Professor has guided so many ME students as well as research scholars in testing the structural elements. He also did fiber reinforced concrete in a great manner. He is well versed in this topic. Now I request Professor Dr. G.S. Triyanam sir to take over the session on advances in fiber reinforced concrete. Thank you, sir.
Thank you for the nice introduction. Good morning to all. Today we will see the recent advances in fiber reinforced concrete, the recent innovation in concrete technology. Of course, the concept of fiber reinforced concrete has been developed during 1970 by the Professor Dr. Ramakrishnan from PSG College of Technology, and he has done a lot of research, and several researches have been taken throughout the world, and at present we are using fibers in not only in reinforced concrete but fiber composite materials suitable for the application of mechanical, automobile, etc. For all fields, these fiber composites can be used. There are different types of fibers available now. Now let us see one by one. Concrete is the most widely used construction material. Despite its versatility in construction, it is known to have several limitations. It is weak in tension, has limited ductility, and a little resistance to cracking. Its permeability is low, its permeability is high. Permeability to liquid is high, and subsequent corrosion of the reinforcement is possible because of this high permeability, and it has poor resistance to sulfate attack. These are some of the major deficiencies. So extensive research in the field of concrete technology has led to the development of special types of concretes which can eliminate to a great degree of these basic deficiencies. The presence of micro cracks at the mortar aggregate interface is responsible for the inherent weakness of the plain concrete. The presence of micro cracks at the mortar aggregate interface is responsible for the inherent weakness of the plain concrete. The weakness can be improved by inclusion of fibers in the mix. So the weakness can be improved or arrested by the inclusion of fibers in the mix. The fibers help to transfer the loads at the internal micro cracks. Such a concrete is known as fiber reinforced concrete. Thus, a fiber reinforced concrete is a composite material essentially consisting of conventional concrete reinforced by fine fibers. So it is nothing but a conventional concrete, but it is reinforced secondarily by the fine fibers, either steel fiber or non-metallic fibers, etc. The fibers suitable for reinforcing the concrete have been produced from steel, glass, and organic polymers. Fibers are available in different sizes and shapes. Fiber reinforced concrete is a two-phase composite material in which cement-based matrix is reinforced with ordered or random distribution of fibers. Regarding to the orientation of fibers, the fibers may be orderly distributed or randomly distributed. If it is orderly distributed, then there is a special name for fiber reinforced concrete such as SIFCON, SIMCON, etc. Or if it is randomly distributed, general name fiber reinforced concrete. The fibers in cement-based matrix act as crack arresters, which restrict the growth of flaws in the matrix, preventing these from enlarging under load into cracks, which eventually cause failure. So, as I said earlier, micro cracks have been developed at the interface between the matrix and the aggregate. These micro cracks have been arrested by means of these fibers, and it delays the cracks, which cause eventually the failure of the structure. It can result in improvement in static properties and dynamic properties of the matrix. Use of mineral admixture, especially silica fume or microsilica, became more popular after the usage of high-range water-reducing admixture. So here in fiber-reinforced concrete, mostly the supplementary cementitious material is the microsilica or the silica fume, condensed silica fume, which imparts the strength to the fiber-reinforced concrete. Because the steel fibers add the strength, at the same time, the concrete, which also improves the strength by means of this cementitious material, silica fume. In FRC, these admixtures produce a denser matrix, resulting in better mechanical properties of concrete. Fibers can be added directly to the mixer once the other ingredients have been uniformly mixed. So fibers can be added directly to the mixer, concrete mixer, once the other ingredients have been uniformly mixed. At the final stage only, these fibers are dispersed into the mixer. The other steps, transporting, placing, and finishing techniques for the fiber reinforced concrete are the same as those used for the plain concrete. So the concrete making process is as usual for the conventional concrete. Only the difference is at the end of the mixing, the fibers are uniformly dispersed, directly added to the mixer and uniformly mixed in the concrete. The other process, transporting, placing, etc. are similar to the conventional concrete. The major factors affecting the characteristics of fiber reinforced concrete are the water cement ratio, percentage or volume fraction of the fibers, diameter and length of the fibers. This length of the fiber divided by diameter of the fiber is known as aspect ratio. So aspect ratio is one of the controlling factor in fiber reinforced concrete. The optimum aspect ratio is around 100. It is proved by the researchers. The location and the extent of cracking under load will depend upon the orientation and number of fibers in the cross section. The fibers restrain the shrinkage and create moments of the unreinforced matrix. This picture shows the fibers, steel fibers. It may be a flat fiber or it may be a wire fiber, crimped wire fiber or the straight fiber, or hooked end fibers. Normally, the hooked end fibers are glued together just like a stapler pin in order to easily handle it. This type of steel fiber is marketed by the brand name Dramix fiber. Dramix is the stainless steel fiber which is available in the form of stapler pin pins. If this glued fiber is dispersed in water, it is automatically splitting into different, individual fibers. Polypropylene fibers and glass fibers. These are the synthetic fibers or the non-metallic fibers. In contrast to reinforcing bars in RCC, reinforcement concrete, which are continuous and carefully placed in the structure to optimize their performance, The fibers are discontinuous and are generally randomly distributed throughout the matrix. As a result, the reinforcing performance of steel fiber is inferior to that of reinforcing bar. You just think about this point. The reinforcing bars are continuous bar. That is, the reinforcement is continuous over a length of about 2 meter or 4 meter, depending upon the length of the member. And it is carefully placed in the structure in the tension zone. Normally, the steel reinforcement is used to take care of the tensile stresses. So, wherever tensile stresses are occurring, you have to place the steel reinforcement. To optimize their performance means you normally need tensile reinforcement, and sometimes you need shear reinforcement and compressive reinforcement, etc., to get the suitable performance. This is for RCC. But here the fibers are discontinuous and are generally randomly distributed throughout the matrix. So because of this, the performance is inferior to that of the reinforcing bars or RCC. So the steel bars are acting as the primary reinforcement, and steel fibers or any other fibers are acting as the secondary reinforcement in fiber reinforced concrete. So fiber reinforced concrete means the role of fiber is the secondary reinforcement. In addition, the fibers are likely to be more expensive than conventional steel bars. Thus, FRC is not likely to replace conventional concrete. However, the addition of fibers in the brittle cement and concrete matrices can offer a convenient, practical, and economical method of overcoming their inherent deficiencies of poor tensile and poor impact strength, and enhances many of the structural properties on the basic materials such as fracture toughness, flexural strength, resistance to fatigue, resistance to impact, and resistance to thermal stresses or spalling of the concrete. These are the properties to be improved by means of the inclusion of fibers. Essentially, fibers act as a crack arrestor, restricting the development of cracks, and this transforming an inherently brittle matrix, that is cement, with its low tensile strength and low impact strength into a strong composite with superior crack resistance, improved ductility, and distinctive post-cracking behavior prior to failure. When you examine the behavior of the FRC beams and comparing the behavior of the RCC beam, the distinction is the post-cracking behavior of the fiber-reinforced concrete beam is significantly different from the behavior of RCC beam. Steel fibers are probably the best suited for structural application. Due to superior properties like increased tensile and bending strength, improved ductility, resistance to cracking, high impact strength, and toughness, and high energy absorption capacity, this fiber-reinforced concrete has found special applications in hydraulic structures, pavements, bridge decks, heavy-duty floors, and tunnel linings, etc. So because of the superior properties like improved ductility, improved resistance to cracking, high impact strength, and high toughness, and high energy absorption capacity, high ductility, etc., this fiber-reinforced concrete has found special application in hydraulic structures, pavements, bridge decks, heavy-duty floors, and tunnel linings, and structural elements which are subjected to seismic behavior. In general, the superior toughness and energy properties of fiber-reinforced concrete in comparison to the conventional concrete improve as volume fraction of fiber increases. You can add the fibers in very little quantity as 0.25% or 0.5%, or moderate quantity as 1% or 1.5%, etc., to improve these performances, superior toughness and energy properties, etc. So whenever the volume fraction of fiber increases, these properties also increasing. Techniques for achieving high fiber volumes, including the strategy of pre-placing fibers in the formwork and infiltrating the bed of fibers with a synthesis slurry. If the volume fraction of the fiber is more than 4%, it cannot be fabricated as just like conventional concrete. You have to fabricate this type of fiber reinforced concrete in a different way. That particular way leads to the development of slurry infiltrated fiber concrete, SIFCON. We will see this SIFCON in a later part of the lecture. Another development is SIMCON, slurry infiltrated matte concrete, is a new generation of high performance fiber reinforced concrete made by infiltrating continuous steel fiber mats with a specially designed cement based slurry. This SIFCON is the randomly oriented distribution of fiber, but in SIMCON it is a ordered distribution of fiber, continuous distribution of fiber. What about the mechanism of fiber matrix interaction? The tensile cracking strain of the cement matrix is very much lower than the yield strain of the steel fibers. As a result, when FRC is loaded, the matrix will crack long before the fibers can be fractured. As a result, when FRC is loaded, the matrix will crack long before the fibers can be fractured. And once the matrix is cracked, the composite continues to carry the increasing stresses. The fibers are able to carry the tensile stresses. So the composite material continues to carry the increasing tensile stresses. The peak stress and peak strain of the composite are greater than those of the matrix alone. During the inelastic range between the first cracking and the peak, multiple cracking of the matrix occurs. So this is a significant behavior of the fiber reinforced concrete. There are number of cracks developed in the load deflection curves. Because of these cracks, the load deflection curves exhibit multiple cracking mechanisms. So until the initial cracking of the matrix, it is reasonable to assume that both the fibers and the matrix have behave elastically and there is no slippage between the fibers and the matrix. Just like conventional reinforced concrete, we are assuming that the steel reinforcement is fully bonded with the cement concrete until the slippage occurs. Until then, this behavior is the elastic behavior. You can apply your strength of material theory. Once there is a slipping occurs, all the tensile stresses from the cement concrete is transferred to the steel reinforcement. So the cement concrete is cracked in the tension phase and the steel tensile stresses are taken by the steel reinforcement. That is the behavior of the RCCB. Similarly here also, until the initial cracking of the matrix, it is reasonable to assume the elastic behavior because there is no slippage between the fibers and the matrix. Once there is a slippage, then the fibers contribute to the tensile strength. In the calculation, you have to account for the tensile strength of the fibers also, fiber reinforced concrete. After the initial cracking has occurred, the composite will carry increasing load only if the pull-out resistance of fiber is greater than the load at the initial cracking. Only if the pull-out resistance of fiber is greater than the load at the initial cracking. So normally pull-out failure is taken place if the strength of the fiber is less. So the composite will carry increasing load only if the pull-out resistance of fiber is greater. In the post-cracking stage, the failure composite is generally due to fiber pull-out rather than the fiber yielding. Before the fiber yielding or fiber fracture occurs, the fibers are, because of the lack of bond stress, the fibers are pulled out from the matrix. So failure will take place due to the excessive cracking. In fiber reinforced concrete, the fracture is a continuous process where the cracking occurs over a wide range of loading and the debonding of fibers occurs over several stages. So multiple cracking mechanism. The bond or pull-up resistance depends on the average bond strength between the fibers and the matrix, the number of fibers crossing the cracks, and the aspect ratio of the fibers. Improvement in structural performance of the fiber reinforced concrete depends on the strength characteristics of fibers, volume of fiber reinforcement, dispersion of the fibers, orientation of the fibers, and their shape and aspect ratio. These are the controlling factor for the improvement of the performance of the fiber reinforced concrete. So behavior of fiber reinforced concrete members. In FRC member subjected to flexure, the load at the first crack will increase due to cracking mechanism of the closely spaced fibers. The load at the first crack will increase due to the cracking mechanism of the closely spaced fibers. After the concrete cracks in tension, the fibers continue to take the load provided the bond is good. After the concrete is cracking in tension, the fibers continue to take the load provided the bond is good. When the fiber strain reaches its breaking strain, the fiber fracture resulting in load transfer to the fibers of adjacent layers, which on reaching the breaking strain fracture and resulting in the shifting of neutral axis. So fibers nearer to the tension face of the beam reaches the failure strain, and this extra strain is transferred to the fiber next to the surface fiber, that is interior of the fiber. So it causes the shifting of the neutral axis. You can notice this behavior in the under reinforced concrete beam. There are three types of behavior: balanced beam, balanced, under reinforced, and over reinforced. In balanced, the critical neutral axis is at one point. Below the neutral axis, tension is taking place, and all the matrix is cracked. All the tensile stresses are taken by the steel reinforcement, and above that only the concrete, above the neutral axis only, the concrete takes care of the compressive stresses, like that. So C is the compressive force taken by the concrete, and T is the tensile force taken by the steel. The neutral axis distance comes into picture, and we are calculating or estimating the moment carrying capacity, etc. Similar behavior here also taking place, but in addition, the steel fibers are taking care of the tensile stresses to some extent. So you have to account for the tensile strength of the fiber reinforced concrete beam also. So that is a compressive force taken by the concrete, tensile force taken by the steel reinforcement, and tensile force taken by the fiber reinforced concrete. Failure occurs when the concrete in compression reaches the ultimate strain. Normally the beams are designed as the under reinforced beams. So the failure occurs because of the compression failure in the concrete. The most important factors affecting the ultimate load are the volume of fibers and their aspect ratio. So volume of the fibers and their aspect ratio is very, very important for calculating these factors. So different types of fibers: artificial fibers, natural fibers, etc. Artificial fibers: steel fibers, polypropylene fiber, asbestos fiber, glass fiber, carbon fiber, polyester fiber, etc. In natural fibers: coir fiber, sugar cane fiber, jute fiber, banana fiber, sisal fiber, basalt fiber, etc. There are innumerous fibers are available, but these natural fibers are having inferior quality than the artificial fibers which are manufactured in the factories. Out of these artificial fibers also, steel fibers, glass fibers, and carbon fibers are high modulus fibers, and polypropylene, asbestos, and polyester fibers are low modulus fibers. We will see one by one in the later stage. Types of steel fibers. Round steel fibers are produced by cutting round wires into short lengths. Round steel fibers are produced by cutting round wires into short lengths. So you take a binding wires of the diameter of 0.25 or 0.3, 0.4 mm, like that, and cut into pieces for a certain length, say 5 centimeter or 4 centimeter, etc. This fiber is the cross section having circular cross section. That is why round steel fibers. These are produced by cutting the round wires, binding wires into short lengths. Next is flat steel fibers are produced by slitting the flat sheet. So for the sheet, layers of sheets are subjected to slitting action or shearing action, and flat steel fibers are produced. Both round steel fibers and flat steel fibers are having the smooth shapes, so bond resistance is little bit less. The other fiber is deformed fiber or crimped fiber, are produced for improving the mechanical bond between the fiber and the matrix. So the bond resistance between the fibers and the matrix will be improved by means of the deformed shape. Just like your tar steel or TMT bar steel, this type of fiber is generally called as crimped fiber. Another classification of fiber is high modulus fiber, low modulus fiber. This high modulus fiber includes steel, carbon, glass, etc. And low modulus fiber include polypropylene and natural or vegetable fibers, etc. High modulus fiber improved both flexural and impact resistance simultaneously, whereas low modulus fiber improve only the impact resistance of the concrete, but do not contribute much to flexural strength. The flexural strength will not be increased by the low modulus fiber because the strength of the fiber is less. Another classification is according to volume fraction: low volume fraction of the fiber, moderate volume fraction, high volume fraction. If the volume fraction is less than 1%, then it is called a low volume fraction. If it is greater than 2%, then it is called a high volume fraction, in between moderate volume fraction. So the low volume fraction means the fibers are used to reduce the shrinkage stresses, shrinkage cracking. These fibers are used in the surface of the slabs, pavements that have large exposed surface area, leading to high shrinkage cracks. So the primary purpose for this low volume fraction is to arrest the shrinkage cracks, which are developed on the large exposed surface, just as roof slab or the pavements, etc. The dispersed fibers offer various advantages of steel bars and wire mesh to reduce the shrinkage cracks. The fibers are uniformly distributed in 3 dimensions, X, Y, Z, making an efficient load distribution. The fibers are less sensitive to cross corrosion than the reinforcing steel bars. Steel bar is continuous in its length, so once corrosion takes place, it will be continuing over the entire length of the steel bar, but these fibers are randomly distributed in between the fiber cement matrix is present, so these are less sensitive to corrosion. The continuity action will not be there. The fibers can reduce the labor cost of placing and the bars and wire mesh. Moderate volume fraction. The presence of fibers at this volume fraction increases the modulus of rupture, fracture toughness, and impact resistance. These composites are used in construction methods such as shotcrete, fiber shotcretes, and in structures that require energy absorption capability, improved capacity against delaminations, falling, and fatigue. So the moderate volume fraction of the fiber, steel fibers or any other fibers, can be applied as a fiber shotcrete, which is used in lining of the tunnels, etc. Similarly, this moderate volume fraction is used in the structures that require the flexural behavior or seismic behavior of the structure, which demands for ductility and energy absorption capacity, and improved capacity against delamination in the case of aggressive environment and spalling of the concrete, and fatigue strength, which is subjected to the reversal of stresses. High volume fraction. The fibers used at this level lead to strain hardening of the composite. Because of this improved behavior, these composites are often referred to as high performance fiber reinforced concrete, HPFRC. In the last decade, even better composites are developed and are referred to as ultra high performance fiber reinforced concrete, UHPFRC. Now the current research is focused on this high performance fiber reinforced concrete. Normally high performance concrete, HPC. This HPC is a brittle material. Because of the higher strength, sudden explosive failure is taking place. So in order to convert this failure into a ductile failure, fibers are added inside the concrete. So this resulting concrete is called as high performance fiber reinforced concrete. This is applied in all field applications. Mechanism: the composites will carry increasing loads after the first cracking of the matrix. If the pull-out resistance of the fibers at the first crack is greater than the load at the first cracking, at the cracked section the matrix does not resist any tension and the fibers carry the entire load taken by the composite. With an increasing load on the composite, the fibers will tend to transfer the additional stresses to the matrix through the bond stresses. This process of multiple cracking will continue until either failure or the accumulated local debonding will lead to fiber pullout. So fiber pullout or fiber failure. Until then, the multiple cracking mechanism occurs and the load carrying capacity increases. According to the report by ACI committee, the total energy absorbed in fiber debonding as measured by the area under the load deflection diagram before complete separation taking place is at least 10 to 40 times higher for fiber reinforced concrete than for plain concrete. Minimum of 20 times increase in the energy absorption capacities available for the fiber reinforced concrete. The magnitude of improvement in toughness is strongly influenced by fiber concentration and resistance of fibers to pull out, which other factors such as shape or surface factor. So the magnitude of improvement in toughness is strongly influenced by the fiber concentration or the volume fraction of the fibers. Similarly, the resistance to pull out. There is a bond stress. Now, another important thing is the role of fiber size. To bridge the large number of microcracks in the composite under the load and to avoid large strain localization, it is necessary to have a large number of short fibers. As I mentioned earlier, the fibers are acting as a crack arrestor. So the main role of the fiber is arresting the cracks. So to bridge the large number of microcracks in the composite under load and to avoid large strain localization, it is necessary to have a large number of short fibers. The fiber length may be 2 mm or 1 mm like that. The uniform distribution of short fibers can increase the strength and ductility of the composite. The long fibers are needed to bridge discrete macro cracks at higher loads. So once developing the micro cracks into macro cracks, we need long fibers to bridge the cracks. However, the volume fraction of long fibers can be much smaller than the volume fraction of short fibers. We need not provide 2% or 1%, 1.5% volume fraction of the long fiber because the long fiber means the length of the fiber is about 5 cm or 6 cm. It produces complication in fabricating the casting the concrete at the site. So the long fiber means the volume fraction of the fiber is reduced to 0.5% or 1%. Whereas the short fiber, it may be 1 or 1.5%. Because the very smaller length, it will not affect the workability of the concrete. The presence of long fibers significantly reduces the workability of the mix. Durability. When well compacted and cured, concretes containing steel fiber seems to possess excellent durability as long as fibers remain protected by the cement paste. When well compacted and cured, concretes containing steel fibers seem to possess excellent durability as long as fibers remain protected by the cement paste. Only the fibers exposed on the surface will be corroded, but the interior fiber are giving the excellent durability. In most environments, especially those containing chloride, surface rusting is inevitable, but the fibers in the interior usually remain uncorroded. Long-term tests of steel fiber reinforced concrete and the durability showed minimum corrosion of fibers and no adverse effect after 7 years of exposure to de-icing soil. So, after 10 years exposure to severe environment, etc., also, there will not be any significant corrosion or significant deterioration of the concrete, etc. So, it is a highly durable concrete. Fiber reinforced concrete is highly durable. If you consider the glass fiber, ordinary glass fiber cannot be used in Portland cement mortars or concrete because of the chemical attack by the alkaline cement paste. The pH value of the cement paste is around 13. So this alkaline nature will affect the siliceous nature of the glass fiber and the chemical reaction will take place and finally the fibers are vanishing. So you should not use the ordinary glass fiber. But zirconia and other alkali resistant glass fibers possesses better durability to alkaline environments, but even these are reported to show a gradual deterioration with the time. After 2 or 3 years, deterioration may take place. Initially, there is no deterioration because of the alkali resistant glass fibers, but at the later stage, after 5 years or 6 years, there will be a gradual deterioration. Similarly, most natural fibers such as cotton and wool or coir fibers or jute fibers, etc., or vegetable fibers, and many other synthetic polymers, fiber, polyester or polypropylene, etc., suffer from lack of durability to the alkaline environment of the Portland cement paste. So, for improving the durability of fiber reinforced concrete, you should not use these natural fibers or synthetic fibers which are decomposed during the passage of times. According to the report of ACI Committee 544, steel fibers improve the ductility of the concrete under all modes of loading, but their effectiveness in improving strength varies among compression, tension, shear, torsion, and flexion. So this is an important conclusions and reported by the ACI committee. The steel fibers improve the ductility of the concrete under all modes of loading. So the improvement of ductility which are demanded by the seismic behavior of the structure or wind, the behavior under the cyclone or hurricane, etc., which demands large ductility, you have to go for steel fibers. But their effectiveness in improving the compressive strength or tensile strength or shear strength or torsional shear strength or flexural strength, etc., are very low compared to this ductility. Even the ductility improvement is 100% means this improvement in strength is only 25 or to 30%. A concrete beam containing steel fibers suffers damage by single or multiple cracks with increasing deflection. So this FRC beam suffers multiple cracking mechanism and the deflection is increasing. In glass fiber reinforced concrete, the mechanism that is primarily responsible for the strength and ductility is fiber pull. Glass fiber surface is a smooth surface, so the failure mechanism is due to the fiber pull. So the primarily responsible for the strength and ductility is fiber pull. Polyester fibers used in concrete to control plastic shrinkage induced bending. This polyester fiber is also similar to the glass fiber, smooth surface. So fiber pullout is coming, but this polyester fiber is having very low strength, and it will not be contributing to the improvement in tensile strength or flexural strength or ductility, etc. But it contributes to the action of crack arrestor. So the polyester fibers such as Recron 3S fibers are used in concrete to control the shrinkage-induced cracks. Shrinkage crack in plastic, shrinkage cracks or drying shrinkage cracks, etc. So in the field practice, construction field practice, if you start the working of plastering over the wall, brick wall, etc., this cement mortar is reinforced with polyester fibers, Recron 3S fibers having about 6 mm length or 12 mm length, etc. These fibers are mixed in the water, and then that particular water is used for making the making the cement plaster. If you apply the cement plaster over the surface of the wall, you cannot notice the cracks, shrinkage cracks in the plaster. Otherwise, the shrinkage cracks are compulsorily appearing because of the evaporation of the water or setting action of the cement paste. So in commercial practice also, these polyester fibers are used. 125 grams per bag of cement is normally adopted. According to the experimental investigation, it is proved that 25% increase in compressive strength is obtained if the volume fraction is for the low volume fraction of the fibers, less than 1% volume fraction of the fiber. If the volume fraction is moderate, you can achieve 40% increase in compressive strength, etc. But the moderate increase in compressive strength is available only 20 to 30, etc. The increase in fiber content results in an increase in the energy absorption capacity. But the volume fraction of the fiber is increased means you can achieve 100% increase in ductility, 100% increase in energy absorption capacity, etc. 0.75% volume fraction and 90 aspect ratio of the fiber produces 30% increase in flexural strength. So normally the fiber reinforced concrete, the volume fraction of the fibers, steel fiber is limited to 1%. The optimum volume fraction of the fiber is about 1%. You need not provide 1.5 or 2% fibers, etc., because it will not act as it will not contribute to the improvement in the strength and durability properties. Advantages of fiber reinforced concrete. Steel fibers result in more homogeneous mix in concrete. Flexural strain capacity is enhanced. It adds ductility to concrete. It controls the cracks. It provides joint stability. The narrow joint width is possible. Shear load transfer mechanism is there. Fatigue and impact resistance is high. Post-crack ductility behavior is there. Once after the cracking is occurred, the ductility is increased very much beyond 100%, 200%, 300%, etc. because of the large deformation. Ductility is defined as the ability of the concrete to undergo in a concrete member to undergo inelastic deformation while sustaining the load. So inelastic deformation is very much higher in fiber reinforced. It reduces the material consumption and saves cost, longer service life. Applications of fiber reinforced concrete. The superior properties of steel fiber reinforced concrete have found it an ideal material for overlays and overslabbing of the roads, pavements, concrete pavements, airfield and bridges. That is also a pavement. Industrial and other flooring units subject to wear and tear and attack due to chemical attack. This industrial and other flooring units, you need not provide steel fibers. This Recron 3S fibers or any other polymeric fibers are sufficient to produce the improvement in wear and tear, improvement against wear and tear abrasion. and attacked to the resistance to the chemical effect. Resistance to the chemical effect. Application of the steel fiber reinforced concrete, highway and airfield pavements, hydraulic structures, tunnel lining, industrial floors, bridge decks, refractory concrete, precast applications, structural applications, etc. In hydraulic structures, the major advantage of using FRC in hydraulic structure is its resistance to cavitation or erosion damage by high velocity water flow. That is, in the portion of the spillway of the dam and stilling basin of the dam, you can use fiber reinforced concrete instead of ordinary conventional concrete because the impact action and the abrasion action of the water flowing at a high velocity is possible. So resistance to cavitation and erosion will be appearing only by this fibers. The SFRC have been successfully used in the repair of stilling basin at Karbala Dam in Pakistan. Nowadays, in all of the dams, we are using only the SFRC concrete. So once again, the summarized application: earthquake resistant structures, overlays of the roads, airfield pavement, bridge decks, thin seats, pipes, composite decks, prefabricated shapes, panels, shotcrete, fiber shotcreting, curtain walls, slabs and grade, precast elements, walls, safe wall, impact resisting structures, etc. Another type of fiber reinforced concrete is developed beyond 2000. This is called as ductile fiber reinforced cementitious composite. Ductile fiber reinforced cementitious composite (DFRCC) is a broader class of materials that has properties and superior performance characteristics compared to conventional cementitious materials such as concrete and FRC. These have unique upper properties including the damage reduction, damage tolerance, energy absorption, crack distribution, deformation capability, and delamination of resistance. Because of these improvements, the name is indicated as ductile fiber reinforced concrete. Ultra high performance concrete is a high strength, high stiffness, self-compacting and ductile material which formulated by combining Portland cement, silica fume, quartz flow, fine silica sand, high range water reducer, water, steel or organic fibers. So high performance concrete is classified as ultra high performance of concrete because of the higher stiffness, higher self-compacting nature and higher ductility, and this higher ductility is produced by means of the inclusion of fibers inside the concrete, high performance concrete. And it is formulated by cement, microsilica and filler material, quartz powder, fine silica sand, high range superplacers, high range water reducer, that is slow superplacers along with water. The materials for UHPC, ultra high performance concrete, are usually supplied by the manufacturers in a 3-component premix: powders and pre-powders, superplasticizer and organic fibers. This powder is composing of Portland cement, silica fume, quartz powder and fine silica sand. This powder is the fine powder, that is the cement and fine aggregates are pre-blended in bulk bags. Cement and fine aggregates are, that is the mortar. Cement mortar is available in the bulk bags, 25 kg bag or 40 kg bags, etc. In this powder, some siliceous materials, some cementitious materials are used. That is quartz 4 is the quartz powder, siliceous material, and the cementitious material, silica fume or the microsilica, and fine silica sand as the silica material are added to improve the properties or durability of the superplasticers. Second, to improve the workability of the concrete, and steel or organic fibers are to induce the ductility. So the fabrication or the casting is easy. You just mix the powder with required amount of water with superpluses, and the fibers are randomly distributed over this matrix. It produces the ultra high performance concrete. This is a reactive powder concrete, RPC, just like this. Fine material, coarse aggregate is not allowed. Slurry infiltrated fibrous concrete. Sifcon is produced by infiltrating cement slurry into pre-placed steel fibers in a form 1. It has to be noted that it does not contain any coarse aggregate but has a high cementitious content. So Sifcon is nothing but the slurry, cement-based slurry is infiltrated through a bed of fibers in a formwork. The formwork may be a cube or cylinder or slab or beam or column or foundation, anything. So once the formwork is ready, you have to sprinkle the fibers to form a fiber bed. After completing the volume of the mold, formwork, cement slurry, flowable cement slurry is poured or made infiltrated into the formwork. The resulting product is Sifcon. Another is slurry infiltrated mat concrete is similar to Sifcon but uses pre-placed fiber mat instead of steel fiber. So the pre-placed fiber mat is available in the factory, just like a glass fiber mat. You can procure this steel fiber mat and cut into required shape and place it in the mold up to the required depth, and then slurry is poured in over the pre-packed fiber mat. This resulting product is Sifcon. The performance of Sifcon is superior to this performance of Sifcon. The steel fibers are pre-placed in the mold to its full capacity, thus forming a fiber network. This fiber network is then infiltrated by cement-based slurry. Due to this method of fabrication, the volume fraction of fibers can be very high, ranging from 4 to 20%. Normally, 10% volume fraction is adapted easily. Beyond that 10% means the flowability of the slurry is very, very thin. You have to add superplasticity along with the VME, etc., etc. So for normal purposes, 8% or 10% volume fraction is sufficient. This is a function of several parameters, including size, shape, aspect ratio, orientation, and method of packing, and extent of vibration, etc. Sifcon is made by pre-placing salt fibers followed by the infiltration of a dense cement-based slurry. Since fiber orientation cannot be controlled, a much higher volume fraction is necessary to achieve behavior like that of Sifcon. Sifcon is manufactured by pre-placing continuous fiber mats followed by infiltration of a cement-based slurry. It is a comparison. The fiber mats are pre-woven and delivered to the site in large rolls. The mats need only to be cut and unfolded into the format. 5% volume fraction of the Sifcon produces around 16 Newton per mm² as the direct tensile strength, whereas 12% volume fraction of the fibers are needed in Sifcon casting technique, and it produces about 14 Newton per mm² direct tensile strength. So 5% is sufficient for producing a required tensile strength, whereas you need 12%, more than twice that of the volume fraction in Sifcon casting technique. So if the steel fiber mat is available, you can go for Sifcon. There is a very good research opportunity in doing the research on Sifcon material. Sifcon beams reinforced with mild steel bar reinforcement have much flexible strength and flexure toughness than that of the conventional RCC. As I mentioned earlier, the steel fibers or any other fibers are acting as secondary reinforcement only. The primary reinforcement is the steel reinforcement, regular steel reinforcement, that is the mild steel bar or cross steel bars. So Sifcon beams reinforced with mild steel bar reinforcement have much flexural strength and flexural toughness than that of the conventional RCC. Sifcon beam column connections absorb much more energy and sustain much higher loads compared to normal curing. normal concrete. The typical properties of SIFCON, as per the literature, is unit weight of the SIFCON is similar to the unit weight of the concrete, but there is a slight variation depending upon the volume fraction of the fibers. If the volume fraction of the fiber is about 4%, 21 kilonewton per meter cube, because it will not contain the coarse aggregate. So it's a slight decrease in unit weight. But if the volume fraction of the fiber is 10 or 12 or 14%, then it produces higher density, about 32 kilonewton per meter cube, because steel is having higher unit weight. So the unit weight of the concrete is approximately 25 kilonewton per meter cube, similar to that of RCC. Typical compressive strength, approximately 190 Newton per mm square or 200 Newton per mm square. Typical tensile strength, 14 Newton per mm square. Typical flexural strength, 76 Newton per mm square. Just you compare with ordinary concrete. Ordinary concrete means you take M20 concrete. The compressive strength is 20 Newton per mm square. Here 200 Newton per mm square, 10 times more than the M20 concrete. The typical tensile strength is 1 Newton per mm square for M20 concrete, but here the tensile strength is about 14 Newton per mm square, just 10 times, greater than 10 times. The flexural strength, the 4 Newton per mm square for M20 concrete, the flexural strength FCR. But here for SIFCON, the typical flexural strength is 76 or 80 Newton per mm square, 20 times more than that of. So the contribution of fiber is significantly experiencing by means of flexural strength. Large amount of flexural strength is there. Flexural tensile strength. Shrinkage strength is very, very low, and the fatigue strength is very high, 90% static strength up to 2 millions of seconds. In the laboratory investigation, a comparison is made. In IRTT, we done the experiment during 1998 as a part of BE project. The cube strength of the concrete for normal concrete is 32 Newton per mm square, 37 or 38 Newton per mm square for fiber reinforced concrete, about 10% increase in compressive strength. For SIFCON also, it is the very low values, about 46 or 50 Newton per mm square. So the contribution of fiber SIFCON in compressive strength, cube compressive strength or cylinder compressive strength is little, about 25% increase in that. Cylinder compressive strength 27, 31, 35. Whereas you compare the tensile strength, split tensile strength, 2.6 for normal concrete, 3.8 for fiber reinforced concrete, about 30% increase, and SIFCON 7.6, 3 times more than that, 2.6 and 3.6, 7.6, about 3 times. The flexural strength, direct tensile strength contribution is about 3 times. The flexural strength 4.5 Newton per mm square, 5.9, significant increase, about 10% or 20%, but SIFCON about 10 times. Abrasive index 66, 40, and 18. So it is resistant to abrasion. This test is carried out in Doris abrasion testing. Impact strength, aggregate impact test. Number of blows causing the failure of the cube is 1 in the case of normal concrete, whereas for fiber reinforced concrete it needs about 20 blows. But for SIFCON cubes, even after 600 blows, there is no significant deformation in the cube. So the impact strength is very, very high in the case of SIFCON material. Because of these superior properties, it can be applied for all types of applications. Security walls that need protection against blasting, drilling, and fire. Nowadays, you come across through news media, paper media, etc. There are a lot of thefts by breaking the safety walls in the banks, ATMs, etc. Because the thieves also bring the welding machine or blasting equipments or drilling equipments like that. But if the safety vault is security vault is built by using SIFCON, the steel fibers are randomly distributed throughout the concrete, so blasting will not be possible. Drilling is also not possible. If at all fire happens, this fire is not producing any ultimate damage because it is a composite material of steel and concrete. Steel is strong in taking the temperature up to 1000 degrees of centigrade. So no damage is occurring to your safety vault. Your money or any other valuable product is safe if you've done your security vault by means of SIFCON construction. The same thing, explosive resistant containers for storing materials that could accidentally explode. So for nuclear reactors or chemicals, harmful chemicals, explosive chemicals, flammable, etc. For storing purposes, you can construct the container by means of SIFCON. Repair of structural components such as damaged pre-stressed concrete beams, bridge deck rehabilitation, pavement rehabilitation, etc. So this repair and rehabilitation procedure is done easily with the SIFCON material. Abrasive resistant surfaces in places such as scrap yards, precast products for rapid repairing, refractory applications, etc. These are the probable application of the SIFCON material. In Singapore, one defense application is that it is a sandwiched SIFCON with ferrocement. The outer side of the wall is made with ferrocement, but the inner part is not hollow, it is filled with the SIFCON material. So the sandwich SIFCON laminate will impart all types of damages, disasters. So it is a disaster-free structure, proof structure. This element is fabricated because of the Professor Dr. P. Paramasivam in National University of Singapore. Experimental investigation of RC frames with the SIFCON beam column joints. That is my PhD work. 2 by 5 story frame. This is the mode. It is a reinforcement grill. This reinforcement grill is designed according to IS 456 and detailed according to IS 13920 detail. Earthquake resistant structures. There is a close-up view of the reinforcement. The column reinforcement is taken into the foundation. The beam reinforcement is taken into the columns, satisfying the development length criteria, LD plus 10 times the diameter. The top bar of the beam is taken inside, and the bottom bar of the beam is taken on the upside of the column. So it gives anchorage to the steel reinforcement, satisfying IS 13920 detail. This reinforcement grill is provided with attachments. Steel stud is fixed to the reinforcement for measuring steel strain, tensile strain in the steel or compressive strain in the steel reinforcement. In order to protect the steel studs from binding of the cement matrix, free expansion should be needed. So it is covered with flexible material hose pipes, rubber tubes. The steel fibers are round steel fibers. Actually, we are producing these steel fibers by being a cutting machine, cutting into a rectangle length, 5 centimeter fibers. These are the binding wires, stainless steel wires having a diameter of about 0.5 mm. It is available in the roads, binding wires. Casting of SIFCON frame. First, the frame mold assembly is there. The cover concrete is done with the SIFCON material, pre-packing of the fiber bed to make the cover concrete. This fiber bed is inside the foundation also. The bottom column is completely made with SIFCON material, and the other portion is at the junction only, beam column junction only. The reinforcement is taken and placed over the cover concrete. So that is the view. And once the reinforcement is placed in the mode, steel fibers are randomly distributed in between the gaps of the reinforcement, mainly on the stirrups, ties. The steel fiber packing is done carefully. As much as 8% volume fraction of the fiber is occupied in this procedure. Now the cement slurry is poured. The cement slurry is manufactured here. Cement and fly-ash material and fine sand materials less than 300 micron size is made into a slurry form, liquid form, and this liquid is poured over the fiber bed to make the cement concrete, stiff concrete. And in between this steel fiber bed stiff concrete, regular concrete, M20 concrete is placed on the beams and columns. And this concrete is compacted by means of needle bend. This is our guide, Dr. P. Govindan from CIT. This laboratory is structural engineering laboratory in CIT. These are our BE students at the time, helping me to do a project, experimental one. So after casting the specimen, curing is done as per the normal practice. Because of the larger size of the frame, gunny bag curing is adopted, and these gunny bags are wetted frequently 3 times a day like that. 20 days curing is adopted. After 20 days curing, these frames are taken, lifted up by means of electric overhead cranes, UVT cranes, and shifted to the testing platform, transported to the testing platform. And over the platform, pre-packed steel fiber foundation is there. This is the reinforcement details for the foundation, precast foundation. And this is the view of the precast foundation. This precast foundation has a slit in between 2 arms. In this arm, in this slit, the frame specimen is fitted and it is jointed to the foundation by means of the bolts. There are 4 bolts for each column and in the middle portion. This precast foundation block is anchored to the strong floor by means of these bolts. So this is completely rigid. This is the strong floor, and this precast foundation is strongly anchored to the foundation, strong foundation. Now the frame is transported to the site and lowered down inside the slit of the precast foundation. After complete inserting, the steel rods, 50 mm diameter steel bolts are provided for the fixity of the foundation. So you can notice the steel bolts, 50 mm diameter steel bolts, for fixing the framed structure to the foundation. This is the view after the fixing, but it later whitewashed and marks have been formed in order to facilitate the measurement of the steel strain, compressive strain, and notifying the cracks, etc. It has to be measured. S means Sefcon frame, left beam, right beam, this beam 1, beam 2, beam 3, beam 4, beam 5, etc. Similarly, column LC, left, middle column, and the right column, 1, 2, 3, 4, 5, etc. These are to be notified in the surface painted mark on this surface. Loading arrangements, hydraulic jacks, push-pull jack or double-acting jacks are manufactured in Coimbatore itself, and these jacks are used for applying the loads in both the direction, positive x direction and negative x direction, push and pull. These attachments are used for applying the loads. The distances make up by these attachments, coupler arrangements. And for acting the jack, hydraulic jack, the oil pump is here. This oil is distributed by means of the distributor. Simultaneously, these three jacks are acted together. The load is applied to these three jacks simultaneously, and same load is observed for all the loads. Load 1, P1, P2, P3, P1 equal to P2 equal to P3. That is the loading arrangement. In order to take the measure, we have done a platform over a certain interval because the total height is about 30 feet. We cannot go up to the top. So over that we are preparing a scaffolding arrangement, and we can climb this scaffolding arrangement and take the measurements, etc. And for measuring the deflection, the initial deflection is measured by means of deflectometers, by means of LVDT, by means of LVDTs fixed at the points, story 1, top, 4th, 3rd, 2nd, 1st, etc. The lateral deflection is measured, LVDT, and once the deflection is exceeding the limits of LVDT, that is normally 20 mm deflection can be measured by means of LVDT, and beyond 20 mm, we are fabricating one deflectometer like this, and these deflectometers are used for measuring the deflection. What is the action of this deflectometer? An inextensible thread is connected at this point by means of pasting, and if the frame deflects, this wire is tending to move and it moves over the spindle. A counterweight is located here. Because of the counterweight, it rotates the needle, and the reading contribute to the deflection. It is calibrated such a way that 360-degree rotation means 360 mm like that. So that is the instrumentation arrangement. We are applying the reverse cyclic load, positive direction and negative direction. So one positive and one negative direction contributes the one cycle of the loading. Similarly, number of cycles of loadings are applied. This is the loading sequence diagram simulating the seismic action of the load. You can notice the acceleration spectrum or velocity spectrum or displacement spectrum. It will be like this, just like this. So similar action will be done here also. Load sequence, seismic loading. And we are calculating base shear as P1 plus P2 plus P3, the total base shear. It is applied at the end of the base, bottom of the base, and top story deflection. We are plotting only here with the top story deflection like this. The load deflection diagram is like this. That is a hysteretic diagram. And from this load deflection diagram, we are calculating the ductility factor as delta U by delta Y. For example, 31st cycle delta Z1 divided by delta Y, it contribute a ductility factor of 9.22. And the stiffness is taken at a tangent drawn at PU by 0.75 PU level, P equal to 0.75 PU level. The slope of the tangent is giving the stiffness values, and the maximum BCR force is 198 kN at the level of this 31 cycles, and the stiffness calculated is 0.75 PU 148. So 148 kN is the other tangent and calculated as the ratio 2 kN per mm. Stiffness required is 2 kN per mm. Initially the stiffness is higher and goes on increasing the loads in elastic cycle of loading. The stiffness is gradually decreasing. That is called as stiffness degradation. So the load deflection behavior, only the maximum load and maximum deflection is taken and plot like this. It is the typical load deflection behavior of the frame subjected to monitoring load, when subjected to monitoring load. Deflection profile, we are measuring the 5 deflection, 5, 4, 3, 2, 1, etc. First story deflection, fifth story deflection, etc. When you plot the deflection and the profile, 62 kN, 83 kN, 124 kN, 145, 198, etc. The frame is deflecting like this, just like a vibration of the oscillation of the coconut tree or the palm tree during the wind flow. During the wind flow, the tree is oscillating like this. The same oscillation is produced. So that is the vibration or the earthquake shaking. Stiffness degradation like this. Initially, the stiffness is 14 or 16, and finally gradually decreasing to 1 value or 2 value. There is no stiffness at all. The frame is subject to failure action. Ductility is defined as the ability to undergo inelastic deflection while sustaining the load, and ductility factor is calculated as the deflection at any particular cycle to deflection at the yielded deflection. So yielded deflection is measured from this load deflection diagram by drawing a tangent at the first cycle, and at the ultimate one horizontal tangent is drawn by the intersection point is taken as the yielded deflection. Yielded deflection is 18 mm for this particular frame. So delta U by delta Y gives the deflection. Delta 31 by delta Y 166 by 18 9.22 is that ductility factor. So all the ductility factor is called, and this is the variation of the ductility factor. Positive means forward loading, and negative means reverse loading. And if all the ductility values are added together, forward and reverse, then it is cumulative ductility. That is the variation of the cumulative ductility values. The relative energy absorption, the energy absorption capacity is nothing but the area under the load deflection diagram at the particular cycle. So calculate the area of the load deflection cycles up to 40 cycles or 50 cycles like that, and plot with the relative energy absorption kilonewton mm and load cycles. The variation is like this, and if all the relative energy variation is taken summation, that is cumulative energy absorption, it is like this. Beginning of the cycles, a lot of energy is not absorbed because the frame is still in the elastic stage, and beyond that all the plastic hinges are formed, the deflection is much more higher. So automatically the energy absorption capacity is higher and higher. So ultimately it leads to about 200 or 300 kilonewton mm is the total energy absorbed by the specimen. This is the failure pattern. In our structural analysis, you notice the sway pattern of the sway mode of failure of the frames, multi-story frames. This is the sway mode, and plastic hinges are developed at the bed column joints here, and the plastic hinges are developed at the column foundation joints. Bottom story level failure pattern, and in the middle story level the failure pattern is like this. So this is a complete failure pattern of this frame. This is Mrs. Umarani, current professor of civil engineering and Anna-University Structures Division, and our guide Dr. P. Govindan. This is myself, and this frame is RCC frame, controlled frame, and this is made with a Sifcon material, Sifcon frame. You can clearly notice the deflection of this frame deflection pattern. Original pattern is like this. This is subjected to this amount of deflection, yielded deflection, inelastic stage deflection. That is our standing position is the vertical position of the column. Now this amount of displacement, about 300 or 400 mm, 40 centimeter, up to 700 mm deflection is also possible. Because of this joint failure, shear strength is very much higher. This shear strength is due to push-pull action. So concrete is not having enough shear strength, tensile strength. So automatically all the concrete is built up and spalled off, exposing the reinforcement and the stirrups also. This is the failure pattern of the joints of the head. Whereas fiber reinforced concrete, the failure will not be there because the cracks have been developed, but the fibers are acting as crack arrestor, arresting the cracks will not be widened up like this and leading to spalling failure, spalling of cover concrete. So in Sifcon also the same type of behavior. These patches are nothing but the paintings. We have done the white patching, So this may be and the actual color of the concrete is visible. But these cracks are not widened, only these are hairline crackings, positive cracking and negative cracking, etc. This is the view of the columns like this, failure of the column like this. The plastic hinge is formed. Plastic hinge is formed. This is the failure at the beam column joints. A plastic hinge is developed at the beam column joints. The beam is having enough rotation, etc. So it is a strong column, weak beam concept. Strong column, weak beam concept. Based on this experimental investigation on multi-bay, multi-story RC frames with the SIFCON beam column joints subjected to seismic type loading, the following conclusions are drawn. The use of SIFCON in the hinging zones beam column joints of RC frame subject to the lateral static cyclic loading results in 100% in the first crack load, 100% increase in the cumulative ductility, 100% increase in the cumulative energy absorption capacity, whereas the ultimate load is increased to only a marginal amount, say 20% increase in ultimate load, etc. Smaller crack widths and better resistance to damage. The crack width is very, very small and the resistance to damage is superior as seen in the pictures. The use of SIFCON in the beam column joints of a condenser frame has resulted in better ductility and energy absorption. And these qualities are desirable for structures located in wind or earthquake prone zone. That is the final conclusion. I have presented this paper in IIT Roorkee, and the expert committee, expert professors are evaluating these results and suggest to the government of India in seismic zone 5, if we adopt the fiber reinforced concrete in the beam column joints, we will reduce the collapse of the structure. That is the prevention of collapse in the seismic design philosophy 3, moderate severe earthquake. This can be easily achieved by means of fiber reinforced concrete. Next experimental investigation on hybrid fiber reinforced concrete. This is also on PhD thesis done in IRTT. Conventional reinforced concrete, steel fiber reinforced concrete, fiber reinforced concrete with steel and glass fibers, hybrid fiber reinforced concrete with steel and polyester fibers. This is done by Dr. Muthusamy, former principal of Shakti Polytechnic College. Materials used and post aggregates, water, silica fume, superplasticists, steel fiber, glass fiber, and polyester fiber. This is the view of the steel fiber, round crimped steel fibers. That is mild steel fibers, not stainless steel fibers, and the Recron 3S fibers procured in the market, and the glass fibers procured in the market. Mixed proportion is for M30 concrete, done by IS 10262. This is the sample of the mixed fiber reinforced concrete mix. Conventional concrete with fibers and the steel fiber concrete 0.75, 1, 1.25, 1.5. That is a variation of volume fraction. And the hybrid fiber reinforced concrete, we take the optimum proportion 1 for all this. And the Recron 3S fibers and glass fibers are used in terms of by weight of cement 0.02, 0.03, etc. Very little quantity because the density is very, very low, so number of fibers are huge enough. Here the density is as much as 8 gram per centimeter square, so the number of fibers are less. So we are equating these two as a fiber input. The details of specimens, beam size, standard by 170 mm by 1500 mm, main reinforcement tomb numbers of 10 mm diameter rods at both the top and bottom, stirrup 6 mm diameter, 100 mm center cylinder. Column size, this thing, longitudinal reinforcement 6 number of 8 mm diameter rods, lateralize. This is a model column, model beam, so the reinforcement diameter is very less, 8 mm or 10 mm. Lateral tie 6 mm diameter shot, 100 mm spacing according to IS 13920 detailing for the beam column joint. The beam column joint is taken as a model of the prototype frame analyzed by using StarPro software, and the model calculation is like this. This is the prototype of the actual building, and this is the 1/5 model of the size. We are taking the size of the beam and size of the column, size of the beam column joint, etc. So this is the reinforcement details of the beam column joint. 120 by 170 dimension of the beam, size of the beam. It consists of 3 numbers of 10 mm diameter bar on both at top and bottom, because it is a reversible nature of the load cyclically. So both the tension reinforcement and compression reinforcement are same, and 6 mm diameter 30 mm to 60 mm centers as stirrups. Here 60 mm centers, here 30 mm centers up to a depth of 2D. Similarly, up to a depth of 2D, the ties are placed at closer interval, and beyond that, the ties are placed at longer intervals. The reinforcement in the column is 120 by 230 mm size, 8 numbers of 8 mm diameter bars are provided as a longitudinal reinforcement, and 6 mm diameter or 30 mm 60 mm centers are used as a ties. Along with this beam column joint, component specimens, tubes, cylinders, prisms, etc. has been cast and tested while testing the beam column joint. This is the test setup for the beam loading frame. It is tested under 2-point loading in a loading frame. The deflection readings were taken by a dial gauge. The position of the beam was changed for reverse cyclic loading in such a manner that we are not having the push-pull jack for this beam testing, because it involves the fixity of the supports while we are applying the load in the upward direction. So we have changed the position of the beam. Top face become bottom face, bottom face become top face, like that. This is the experimental setup for the beam. The beam is having a dimension length of the beam, and 2-point loading is applied. Screw jack or hydraulic jack is provided, and for the measurement of the load, probing ring is used. Dial gauge is used for measuring the deflection. Normally 3 dial gauges are used, but here the picture shows only the middle dial gauge. That is a test setup for beams, and here the test setup for columns. A cylindrical column is fabricated with conventional concrete and silicone and other things, and this column is subject to axial loading, and the axial strain and the axial stress readings are unplated. This is the arrangement for beam column joints for forward loading and for reverse loading. This is a beam column joint, column portion. This column portion is fixed on the support, and for ensuring the fixity of the support, you can apply a load of about 10 or 100 kN like that, such to ensure the total compressive strength of the compressive stress in the column, 0.1 FCKAC. This is specified by your IS 1893 code. For the multi-story buildings, the column is subjected to normal axial pressure. And in order to simulate this axial pressure, axial load on the column, this load is applied. The beam portion is projecting, and we are applying the load at the end of the beam by means of screw jack, and the probing ring is used for measuring. The deflection dial gauge is used for the measuring the deflection. This is the picture of this loading arrangement. That is the specimen, and the hydraulic jack is used for applying the concentrated load, and the screw jack is used for applying the variable loads over the tip of the beam. Probing ring is used for measuring, and the dial gauge is used for measuring the deflection. Here the jack is done at the bottom face to lift the beam column in the reverse mode, and dial gauge is used for the measuring of negative deflection. The results are plotted like this. For conventional concrete, 45 Newton per mm square, even though it is designed for M30 grade, but we are obtaining, because of the quality control, high quality control, 45 Newton per mm square is the compressive strength for the conventional concrete, and 55 Newton per mm square for fiber reinforced concrete, 61 or 58 Newton per mm square for the hybrid fiber reinforced concrete. Similarly, the split tensile strength 2.8 Newton per mm square, 3.67 Newton per mm square, and 4.27, 3.73. This compressive split tensile strength is improved very much, such as to 30% or 40%, because of the inclusion of fibers. The fibers are acting as the crack arrestor. 30% increase in SFRC, 50% increase in HFRC. Similar flexural tensile strength, the prism specimen are subjected to 2-point loading. We are estimating the flexural strength as PL by BD square, 4.7 Newton per mm square for PCC or control concrete, and 5.9 Newton per mm square for fiber reinforced concrete, and 6.7 Newton per mm square for hybrid fiber reinforced concrete. 25% or 30% increase. As per the literature also, 30% increase in flexural strength is obtained by using 0.75% volume fraction of fibers. Similarly here also. The specimen, cylinder specimens are subjected to the stress strain behavior action by using the compressiometer. We are plotting the stress and strain, that is the stress strain behavior. From this stress strain diagram, we are estimating the modulus of elasticity, initial tangent modulus, and the value is like this. Slight increase in modulus of elasticity. The mode of failure, this is a conventional prism splitting into two pieces, but here there is no splitting action, only the crack is produced. Similarly, in the splitting tensile, vertical crack is developed in ordinary concrete, but here there is no vertical crack, only the hairline cracks are available. These are the conclusions. In SFRC, the number of fibers, microfibers across the cracks is certain and limited, whereas in HFRC, the number of fibers, microfibers is very large, and these are discontinuous fibers provide the link between the microcracks and act as crack arrestor with transferring the loads. That is why the improvement in properties are noted. When the fibers are combined in the form of hybrid, the onset of cracks may be delayed and result in a significant load differential. However, this effect is only marginal and ultimate load stages. Only the steel fiber plays the role of FRC and transfer all the loads. Similarly, this hybrid fiber reinforced concrete specimens are subjected to durability test, RCPT test, chloride RCPT test. That is the cylinders, NaO solution and NaCl. That is the specimen 52 mm thickness specimen. And the electrode is placed and 60 volt current is passed. Every 30 minutes, the Coulomb's readings are taken and total charge passed is calculated, and we obtain the results. If it is greater than 4000, high penetrability of chloride ion is possible, and if it is less than 100, negligible chloride ion penetrability is possible. But here we are obtaining, because of the good quality control, all the concrete specimens are exhibiting only the low quality 1000 to 2000, and HFRC are exhibiting very low chloride penetrability. These recurrent fibers are contributing to the durability of the hybrid fiber rather than glass fibers. So for strength action, glass fibers are needed. For durability action, recurrent 3S fiber is sufficient. This volume fraction is very, very less, 0.01%, etc. This 0.01 with 1% volume fraction of steel fiber gives good results. Hence, the presence of hybrid fibers in concrete improves the chloride and permeability when compared to that with the presence of steel fiber. Behavior for beams, reverse cyclic loading is applied, that is the loading sequence, load deflection diagrams, historic load deflection diagrams, So the load carrying capacity is, first crack load is very much increased, 24, 30, 33, 33, etc. And the ultimate load is slightly increased, 45 to 51, 51, 51, etc. Because the fibers will not contribute to the ultimate load characteristic. It will contribute only the first crack loads. The ductility factor, cumulative ductility factor is also like this. 16 is the cumulative ductility factor for the plain concrete beam, RCC beam, but SFRC is 28 and for HFRC it may be 30. So the energy absorption capacity is 80% higher than that of the conventional concrete beam. Similarly, energy absorption capacity, the area under the load deflection diagrams and the summation of the relative energy absorption capacity produces a cumulative energy absorption capacity 700, 1200, nearly 80% increase, but here 1900 or 1800, about 2.7 times, 2.6 times or 2.7 times, 200 times increase. The energy absorption capacity is very much higher. Fibrous concrete enzymes suspension takes more load cycle to failure, very much higher. So it is suitable for the earthquake resistant structures and wherever reversible stresses are prevalent. That is the failure pattern of the beam, all the beams. Similar testing is done on the beam column joints, that is the load deflection behavior of the beams, the load carrying capacity 18, 24, 27, etc. 27 and 39 kN. The cumulative ductility factor 11, 20, 23, 21, etc. Similarly, the energy absorption capacity 293, 666, 769, etc. So about 100% increase in energy absorption capacity. The mode of failure is also a variable. For RCC, the sudden failure of the beam column joint is possible because this plastic hinge is formed at the beam column junctions and the beam fails. But here, instead of single cracks, a series of hair cracks are visible throughout the beam length, and here it will take more and more load to develop full mechanism, plastic hinge mechanism. For HFRC also, there are a number of series of flexolags, but the ultimate failure is similar to SFRC. Another investigation using natural fibers and vegetable fibers, that is banana fibers. Pseudostem fiber can be extracted after the fruit branch was harvested by using an extractor machine. Banana stem fibers are extracted by initially cutting into lengths of convenient size and peeling layer wise. The individual seeds were dried under the sun for 2 weeks and then they are soaked in water of 2 minutes. Once the lignin and cellulose were separated, the seeds were dried again and the fibers were replanted. That is the sequential operation. Threading machine, and this is the view of the fibers. These banana fibers are nowadays used as a replacement of textile fibers, that is the cotton fibers. So the cotton fibers are mixed with banana fibers or any other vegetable fibers, and our cloths are manufactured, and this is called as eco-friendly cloths. And these cloths have very much demand in the foreign countries, European countries. That is why this banana fibers and sisal fibers are freely available in Tirupur area, where textile industries are very much high. But these fibers will not be used as it is. It has to be treated to improve its surface morphology and fiber mechanical properties. The extra fibers were treated with 5% sodium hydroxide solution for 4 hours under the total immersion condition to avoid oxidation of the fiber, after which it was used in overflowing tap water until natural pH, neutral pH is obtained. The treated fibers were then dried and sunlight for 24 hours to remove the free water and were subsequently cut into the rectangle. So this is the view of the banana fibers. Mixed proportion is adopted as the M30 grade concrete. This is done by using IS 10262 code of practice. The superplast is used as 1.7 kg per meter cube, that is 0.5%, 340 and 0.5%. And the steel fiber initially 0, banana fiber is 0.5 by weight of cement. This is by volume of concrete by weight of cement. And SFRC 1% by volume of concrete, and HFRC 1% and 0.5%. So banana fiber, steel fiber, and hybrid fiber. So the stress strain behavior of the cylinders, concrete cylinder, FRC cylinder is like this. It gives the modulus of elasticity values, the beam testing. Here only the monitoring forward cyclic loading is adopted, not the reverse cyclic loading. The load deflection behavior. Load carrying capacity is 15 kilonewton as the first crack load for the RCC beam. When the fibers are added, 21 kilonewton, just a 50% increase in the load carrying capacity. Ultimate load 45 and 51, marginal increase, about 10% increase. Whereas the deflection is also increased very much, 18.5 mm, 20.6 mm. Because at the inelastic stage, the deflection is very high. Compression of energy absorption capacity 238 and 382. Considerable energy absorption capacity is available in HFRCB. Similar ductile factor 8 and 13, 50% increase in ductile factor is there. Stiffness degradation, both HFRC and RCC are exhibiting the similar type of stiffness degradation. You can notice here the vegetable fibers are having very low modulus. That is why we are not expecting sufficient amount of this stiffness. Conclusion, there was 30% increase in compressive strength as a result of hybridization. Hybridization boosts the spill tensile strength and flexure strength by 45% and 62% respectively. So increase in compressive strength is only 30%, whereas increase in flexure strength is 60%. Similarly, sisal fiber is here. Sisal fiber and caprala fiber. These fibers are manufactured similar to these banana fibers. And alkali treatment is used for strengthening or improving the properties of the fiber. This is the properties of the fiber, 25 mm length, diameter is 0.25 mm, aspect ratio 100, tensile strength is very low, 268 Newton per mm square, percentage elongation 15% elongation, Young's modulus, modulus of elasticity 42 gigapascal, density 1.7 gram per cc. So compressive strength 41 Newton per mm square, sisal fiber is added 44 Newton per mm square, steel fiber 47 Newton per mm square. If these two are added, it results in higher compressive strength 54 Newton per mm square, near about 40% increase in compressive strength. Similarly, spread tensile strength 3.67 Newton per mm square, 5.52 Newton per mm square, near about 50% increase in split tensile strength. Similarly, the flexural tensile strength 6 Newton per mm square for the plain concrete beam and 10 Newton per mm square for hybrid fiber reinforced concrete beam. 50% increase in flexural tensile strength is possible. Similarly, modulus of elasticity is also increased. RCC beams, this beam is cast and tested under the 2-point loading systems. Load carrying capacity of crack load 15 kilonewton, 22 kilonewton, ultimate load 45 and 51 kilonewton. Load deflection behavior of the HFRC beams, very large area is available under the load deflection diagram. That means energy absorption capacity is much more higher than conventional RCC beam. So cumulative ductility factor like this, about 14 and here about 16. So 100% increase in cumulative ductility. Energy absorption capacity 250 and 450, about 80% increase in energy capacity is available. Mode of failure is similar to this. HFRC, there are number of car cracks available, resulting in higher strength. Instead of adding a single type of fiber, the combination of different types of fiber, that is hybrid fibers, increases the ductility and energy absorption capacity substantially. This phenomenon is particularly advantageous in case of structures located in earthquake-prone zones. Another experimental investigation using stainless steel fibers to reduce the corrosion of the steel fibers. Stainless steel fibers are used instead of mild steel fibers, so to improve the durability of the concrete, fiber-reinforced concrete. These properties are like this. Yield strength is, tensile strength is higher, 600 Newton per mm square. Test results indicate that SS of C 47 increase compressive strength 39 and 47, split tensile strength 2.3 and 3.7, flexural strength 3.8 and 5.4. Very much increase in strength properties. And these beams are induced to the corrosion, accelerated corrosion test setup, and it is the schematic diagram. And this is a half cell potentiometer for measuring the corrosion level. This potential are tabulated like this. For the steel fiber reinforced concrete, 245 initial reading, and near about same thing, 266. But at the later stage, in 140 hours, it exceeds the corrosion limit minus 350 millivolts. Whereas here it is within the limit minus 226, and after that it will take more time, and 190 hours it reaches minus 350 demarcation point. Whereas at this point it involves severe corrosion of these fibers. So at the end, this is maintaining the same thing. The propagation is not at all taking place, but here the propagation leads to the failure of the structure, 200 hours. This is the view of the specimens after corrosion. This is a schematic picture representation of the potential versus hours. So initial corrosion is taking place 350 hours. So it needs about 130 hours, but it needs here 190 hours like that. So this much of longer life is possible with the help of stainless steel fiber reinforced concrete. Even at the ultimate failure, here it closely follow the demarkable level 350, 300, 400, etc. But whereas it extends further and further, 700, 800, 900, etc., it leads to complete failure. So stainless steel fiber reinforced concrete is preferable. That is the result: load carrying capacity, energy absorption capacity, and ductility factor. The failure pattern of the stainless steel fiber reinforced concrete beam. The beams are subjected to reversible loading. So cracks, forward cracks, negative cracks, etc. Beam column joints are used for exhibiting the behavior, ductility factor, energy absorption capacity, mode of failure, etc. Beam plastic hinge is formed at the junction of the beam columns. Another experiments with steel fiber and polypropylene fiber. Here HFRC means steel fiber and polypropylene fibers. These are the advantage of hybrid fiber reinforced concrete beams. View of the polypropylene fiber. This is a high, the modulus of elasticity tensile strength is a little bit higher, 1100 Newton per mm square. But modulus is less, so it against polypropylene conform to low, medium modulus fibers. Aspect ratio is 67. Sorry, this one is the steel fiber, crimped steel fiber. This one is the polypropylene fiber. Only the tensile strength is 750. It's much less than steel fibers. The compressive strength is more or less 10% or 20% increase. Spread tensile strength or the flexural tensile strength is 50% increase. Loss of weight is a durability criteria. Loss of weight in acid attack, sulfuric attack is very much less compared, nearly 50% less. So hybrid fiber reinforced concrete is much more resistant to the acid attack. There is a view of the acid attack before and after the immersion. Half cell potential reading, corrosion attack is there. Here also you can notice minus 350 is the demarcation point, and it is having some particular limit. Beam specifications. The volume fraction is 1% by volume and 0.2% by weight. The polypropylene is having very less density and number of fibers are very, very large. So only this 0.2% is sufficient. So conventional concrete beam, that's a first beam. You can notice the energy absorption capacity. First crack load, ultimate load, and maximum deflection. Comparison of ductile factor, energy absorption capacity, stiffness degradation on or similar with the hybrid fiber reinforced concrete, etc. That is the end of our presentation. The summary is, instead of adding steel fibers alone inside the fiber reinforced concrete beam, you can utilize the hybridization principle. Low modulus fiber and high modulus fiber, long fiber and short fibers, macro fibers and micro fibers, depending on the aspect ratio, and metallic fiber and non-metallic fibers, synthetic fibers and organic fibers, vegetable fibers and metallic fibers. These are all combinations, and this combination of hybrid fibers produces a very good result in all the aspects: strength aspect, durability aspect, structural behavior, ductility, energy absorption, stiffness, crack load carrying capacity, etc. So because of this superior properties, this fiber reinforced concrete beam can be applied in many number of applications. Thank you very much for the patient listening. If you have any questions, I am ready for answering these questions up to my knowledge.
Hello.
Okay.
Sir, the session was very nice, sir, and the information that you have shared is wonderful, sir. Sir, my question is regarding crimped steel fiber that we have used. So what should be the aspect ratio that we have to consider to improve the shear strength in case of a deep beam?
According to the literature survey, the optimum aspect ratio is 80 to 100.
80 to 100. Yeah.
80 to 100. But for the crimped fiber, you have to consider the length of the fiber and diameter of the fiber, very readily available in the market.
Yes, sir. Yes, sir. So, sir, one more question is there. Can we use 3 fibers?
Can you use
3 fibers instead of 2 fibers?
3 fiber. You can use. You can use.
Yeah. And
normally 2 fiber means hybrid, 3 fiber and multiple hybrid.
Yes, sir.
But you have to concentrate on the action: low modulus, high modulus, or low strength and high strength, and number of fibers available in the zones. In the micro crack zones, if the number of fibers are thousands of fibers, the cracking resistance is very much higher. If you go for steel fibers, only tens of fibers are available across the crack, so the initial crack load is not be increased so much. So that is why we have to go for low modulus fiber, increasing the number of fibers at this particular point.
Yes, sir. Thank you, sir. One more last question is there. How we can determine that energy absorption?
In the load deflection diagram, the area under the load deflection diagram is taken as the energy absorption, because whenever you is the specimen is subjected to load, some energy is absorbed. What is work done? Work done equal to load into displacement. The same concept is applied here. The area under the load deflection diagram is denoting the energy absorption capacity.
Sir, is there any software available to work out that area?
You can use your AutoCAD software.
Yes, sir.
So draw the load deflection diagram in the AutoCAD, and you can use the tools available in the AutoCAD to find out the area under the particular part.
Yes, sir. Thank you, sir. I'm actually, sir, my project research work is on this topic. That is shear strength improvement of deep beam using multiple fibers.
Oh.
So,
One researcher, Kannan Rajkumar from SRM University, has done the
okay.
shear strength of the fiber reinforced concrete.
Yes,
To
sir.
have a review on this PhD
Yes.
thesis, it will be helpful for your
Yes, yes.
literature review.
Thank you very much, sir. Thank you so much.
Thank you. Any other question? For the benefit of the participants, most of the participants are teaching the concrete technology subjects or the reinforced concrete subjects to your graduate students. While teaching, you have to summarize the benefits of fiber reinforced concrete. Then only the budding engineers, when they are go into the field, they are using this fiber reinforced concrete in the field application. Because I have faced a lot of questions while I am presenting my research paper in various universities and various IITs, etc. What is the practical aspect of this fiber reinforced concrete? It is not up to the difficulty. You can easily manage this fiber reinforced concrete because at the end of the mixing, before dropping the concrete, you just add the fibers inside the mixer and go through 1 minute mixing. That will be sufficient. That is the fiber reinforced concrete. Similarly, the usage of fiber reinforced concrete is not needed at all points of the structure, only where the high bending moments or high stresses are occurring in the regions. So at the central point of the beam, at the support points of the beam column junctions, etc., lot of stress concentrations are there. So in order to take this lot of stress, large stresses, we should adopt for the hybrid fiber reinforced or fiber reinforced concrete. That will improve your ductility and energy requirements whenever these sections are subjected to cyclic loading or earthquake type loading or wind loading, etc. Or even explosive loading. Suppose a hitting impact strength is there or a bomb is blast under the structure, etc. This fiber reinforced concrete is having very good resistance against the explosive action, against the blasting action, against this impact of the accidental collision like that. So because of these improved properties, it is normally needed in the multi-story building structures. Whenever you provide open stories in the ground multi-story building, open ground parking, you need the construction of the bottom story columns with fiber reinforced concrete. Accidentally, when the car is colliding with the column, nothing significant damage is done to the column. It will take care of the damage by means of the resilience, that is the energy absorption capacity. It is a very good point in a fiber reinforced concrete. Similarly, for multi-story buildings, this fiber reinforced concrete is poured only in the beam column junctions, not in the beams or columns. Only at the junctions it is used. So it will be sufficient. So our researchers in IIT have done only in the junctions, even though my topic is only in the junctions. Okay, thank you very much for the present listening and valuable feedback. Thank you. Thank you.
Thank you very much, Professor sir. Professor has covered different types of fibers, that is artificial and natural fibers, SIFCON and SIMCON fiber reinforced concrete, mechanism behind fiber matrix, behavior of FRC members, and applications of FRC. Sir has covered column beam joint in a detailed manner. He also covered natural fibers, stainless steel fibers, etc. Institute of Road and Transport Technology has very good structural testing facilities. In that, SAR has guided many ME students as well as PhD scholars. I request the participants, you can make utilize of him. Whenever you have any clarification, you can contact at any time. Normally, he is interested in helping students as well as research faculties. Kindly make use of him. So thank you. Once again, I thank you, Professor Sir. Thank you very much. Dear participants, next session will start by 11:50 a.m. Kindly join after the little break. Thank you. Thank you very much, sir.
Before conclusion, I will give one more suggestion. I will share the PPT with organizer, and if you interested in going through the soft copy of this presentation, you contact your organizer and get the soft copy. Thank you, sir.
Thank you very much. Thank you.
Praveen, are you ready?